This will be a very psychological lecture. I will try to get you to accept something. So we're talking about integration. And here's what I want to say about integration. Integration is thought of as a very sophisticated topic. But right now I want to talk about the unsophisticated part of integration. And it's the most important part. I call it taxonomy, just understanding where different concepts live and whether a concept is intuitive or a derivative of something and so on. So that's what I want to talk about. And I really want to take mystique. I want to take the mystique out of integration and really present it as something simple and intuitive and also sort things out. So that's the goal of my lecture. And I get asked lots of questions having to do with definitions and theorems, proofs, and so on. And I think a lot of those questions stem from not having a clear picture of precisely what context you're in. And when people are confused, or they think that something simple is complicated, or that something complicated is actually very simple, it's because the speaker and the listener did not agree on the context. So I just want to set up the context for integration. And here's how I want to do it. There are, broadly speaking, two distinct kinds of integrals. Kind number one, which will belong on this half of the board, is the geometric integral. And it will be simple conceptually, let's say very simple in every way. So here's the trade-off of geometric integrals. Very simple conceptually, but not much you can do with them beyond concept and general insight. And then on this board, we'll talk about arithmetic integrals, which is really the only kind of integral that you've encountered in your high school and undergraduate careers. These are integrals that include specific types of functions, such as sine of x, precisely the kind of problem that you would encounter in calculus, and it has no geometric interpretation. It's just an arithmetic exercise. And so that's how my students tend to think of integration, as an arithmetic exercise, which can then later be endowed with a geometric interpretation, as opposed to this side of the board, where it's pure geometry and no automatic way of evaluating integrals. So this was very broad and vague, so let me start clarifying these notions. Here's what an integral is. Think back to the lecture where we talked about volumes, areas, and lengths, and how I said that we cannot define those concepts, but we all agree on what they are, at least on an intuitive level. So geometric integrals are pretty much like that. So one of them would be a volume integral. So here's what a volume integral would look like. We would be integrating some field, f, over a volume. So here's a drawing. We have some three-dimensional domain, right? So this is my shadowing. So you can see that it's a three-dimensional shape. It occupies a certain region in the three-dimensional space. There is a field F defined on it. Maybe it's mass density of the substance that fills this domain. And then the integral would be written this way, and I'll say in a moment what it means. Alternatively, not alternatively, but in parallel, there might be a two-dimensional domain. So this domain is denoted by V. A two-dimensional domain, A, and we might consider an area integral, which will really not be that different. And it would be denoted this way. And finally, we might have a curve. What letter are we going to use for it? I'm going to use L for line. Actually, this one will keep. And it would be an integral over this line of some field defined on the line, and it would be denoted like this. And how do I define it? Well, I'm not going to define it. I'll kind of say what it is, but I won't define it, because recall that we did not define what volume is. we all agreed that we have the same understanding of what volume is. I think there would be some properties that we would agree on. For example, if I were to divide this into two domains, then the total volume is the sum of the two smaller volumes. Same thing for areas, same thing for lengths. I think we would agree on that. Maybe we would agree on a few properties beyond that. Whether these properties are enough to define the concept, I'm not sure. Probably would get close, if not all the way there. But we understood what volume is. So I invite you to understand in the same intuitive way what this integral means. And what this integral means is the total amount of f that occupies this volume. I could have said intuitively that volume is the total amount of space that occupies this space. So right now I'm just saying total amount of f. If f is mass density, then this is total mass. If f is electric charge distribution density, then this represents the total charge. And so on. It's just the total amount of substance or whatever it is that's represented by f. And the same thing here. Whatever f represents, maybe it's once again just a surface and it's a total amount of charge. And f is surface charge density. It's just the total amount of f that's present in this domain. This is in the plane, but I could have also made it a surface in a three-dimensional space. And the same thing here. It's just the total amount of f along the curve. And if you think that this is vague, then I will agree and disagree with you at the same time. What I will say is that it's just as vague as the concept of volume itself. And if you had questioned me about volume, what volume means, well, you didn't really explain what volume means. Can you explain it a little bit more in depth? If you had asked me that question, then it would be equally valid to ask the same question here. What do you mean total amount of whatever represented by f? It's unclear. What I'm trying to say is that it's equally unclear. It's not more unclear. Would you kind of agree with that? And so what usually happens in books is that the concept of volume is accepted on an intuitive level. And even if there is a definition that includes a limit, it doesn't convince me. If it convinces another person, that's great. But math is a very individual, emotional subject. And my emotion is to not be comfortable with it. And I'm not convinced. And then this integral is defined in a way, once again, by some kind of a limiting process that relies on the concept of volume, right? You'll break this up into individual small domains and you'll multiply the value of f at any point within that little section by the volume of the domain of that little section, and then add them all up. Well, that relies on the concept of volume, which to me is equally unclear. So that's all I'm trying to say. I'm not trying to say that this is clear. What I'm trying to say is that the concept of an integral over a domain and the concept of the volume of that domain are either equally clear and equally intuitively natural, or they're both equally unclear or equally challenging, and so on. That's the only point that I'm trying to make. And since I was able to tell you that we can't define volume, but we can work with it anyway, and you seem comfortable with moving on then, I hope that you will be equally comfortable moving on now. Okay? So that's what a geometric integral is. And of course, I could say the exact same thing about a surface integral and about a line integral. What's appealing about this? First of all, such a simple definition. You know how simple this definition is? There is no definition. It's the simplest definition of all. We're saying we're not really defining it, we're just moving on. So that's as simple as it gets. Also, there are no coordinates. There are no coordinates in the ambient space at all. It's purely geometric. Sometimes I like to use the word physical because you can say, well, mass density is not a geometric quantity, it's a physical concept. I'm fine with that. So I would call these geometric / physical integrals. So that's the benefit, right? You can talk about these things without a reference to coordinates or arithmetic integrals or anything at all. So ancient Greeks could have easily had these concepts, and they pretty much did. We'll talk about Archimedes in just a moment. But on the flip side, how would you actually evaluate it, right? Integrals, we know from calculus, we want to evaluate them and get a number, right? In each of these cases, it's a number. And you can also integrate a vector quantity, the exact same definition. It doesn't change anything, right? Actually, when we discuss this in a moment, we won't be able to integrate vector quantities because you've never seen anything like this, right? This is just not something that works arithmetically. You would need to break it down into components and then do it component by component in an arithmetic sense, right? But here, there is no conceptual difficulty in the quantity f being a vector quantity. You just add up all the little vectors, right? So it works the same way. And you might ask the question, well, how do you evaluate it? Very valid question. And my evasive non-answer is, well, you didn't really ask me that question. We were just talking about volumes. And you didn't ask me that same question about areas or lengths. Well, how do you actually evaluate it? Okay? So just remember that. I'm not saying that makes the question less valid. You could have asked me that question. It's all about moving forward. Like, are we acknowledging enough to move forward? Okay, so that's a fundamental question, and it remains, and I will begin answering it today. So that's one answer. And then another answer is you can let your ingenuity fly, and you can let your creativity shine. And you can just get very, very creative with this. For example, if you were integrating mass density, and so the answer is the total mass, right? Then you can use a scale, right? A balance scale, right? You know, like the classical thing like this, right? That's an integration machine. It integrates mass density by using some reference weights that you put on one side and the object that you're trying to integrate the mass density over on the other side. Yeah, there you go. I just evaluated this integral where f is mass density, right? That's fair, right? It's very creative, right? And if you had asked me the same question about volume, well, I would have said the same thing. Let's get very creative. And you can get creative in ways that are just creatively creative. For example, you know the famous legend about Archimedes, who was asked to measure whether a crown was made of pure gold or not. So how do you measure the density? Well, you have to measure the volume, and you have to measure the mass. So you have to measure this integral, and then divide it by volume. Both are a challenge. And so the mass part of it could maybe be solved with a scale, where you put cubes of gold on one side and the crown on the other. And so you can measure the mass effectively in the units of cubes of gold. And then how do you measure the volume? Well, that's a very interesting question. So apparently, according to legend, I have nothing to draw. I don't know what I was hoping for. Archimedes was taking a bath, and he realized that when he gets into the bath, he displaces a certain amount of water, and that amount of water equals his volume. So all he needs to do is submerge the crown in water and see how much water it displaces in a very regular shaped container. And there you go, you have the volume. But what did he do? Well, he found volume, or he integrated 1 over the volume, right? That's very creative, right? And so that caused them, according to legend, jump out of the bathtub and run through the streets of Syracuse shouting "Eureka," which means "I've got it." Make sense? It's obviously just a legend, but what he figured out in terms of what I've presented here is he's figured out how to integrate 1 over the domain of the crown. And he did it in a very, very elegant way. Does that lead to a rigorous definition? I don't think it does. I think it'll be circuitous. Like if you define volume this way, if you say, okay, I'm a physicist, that's my starting point. Let me define the volume of anything as the amount of water that it displaces. And then I would say, why water and not air? And you would say, well, because water is incompressible and air is compressible. And I would ask you, what does incompressible mean? And you would say, where it doesn't change mass per given volume. And then I would say, well, what's volume? And you'll say, well, volume is the amount of water that you displace. And do you see how you're instantly in a circuitous logic and you can't define it? So that doesn't define anything. It doesn't help you find the ultimate starting point. It all starts in the middle and is suspended in the clouds. That's just how math is. And anything else is a delusion. So it all starts in the middle. But yeah, you can get creative. And of course, you can get very creative. And we've experienced it in this class already by subdividing the domain into smaller parts and adding up the small parts. And that was Archimedes' method of exhaustion. And he calculated the area of a parabola and circle and sphere, the area of a circle, volume of a sphere, and everything fell to the power of imagination and creativity and just genius and skill. So yeah, this is the world that requires ingenuity, but with ingenuity you can move forward. And yeah, if you were to press me on the most practical way to evaluate an integral like this, I would go for the method of exhaustion. I would say, let's just subdivide it into smaller parts like we did with a parabola and add them up. Except in the case of an integral, I would take the area, in that case it was a triangle, the area that I can calculate because we had previously squared the triangle. Here I would also have to multiply it by the value of the field we're integrating at any point inside that triangle. So that would be an additional kink. And I can probably think of a problem that we could solve even if f is not constant by the method of exhaustion. But yeah, you have to get creative. And you have to also have the ability to move forward without any definitions. So that's geometric vectors. You should find as many statements as you can that can be stated in terms of the concepts that I have on this board. And let me mention a few. For example, consider, let's be here, works for volumes and areas, but let's have a domain A. Its boundary is a line. As you know, we just discussed it, it comes endowed with the concept of the outward normal, a very well-defined quantity. And so with what I have on the board, I have enough to answer the following question. What's the integral over the boundary, the entire boundary, of the unit normal? I don't know why my voice went up. That's the end of the question. Of the unit normal. What does this equal? Yeah, what do you think? Of course they cancel, right? They all point in different directions, right? If you think of this as just strings pulling it in all the opposite directions, it's not going to move anywhere. In fact, the physical intuition is these are all with a minus sign. The forces of pressure, if you take this balloon and you put it into a uniform pressure field, pressure acts in the direction orthogonal, this will be with a minus sign, to the surface. And because the pressure field is uniform, all of these forces will be the same. Which way will the balloon go? It won't go anywhere, right? It can't start floating. It would violate every intuition and also law of physics, which is based on our intuition and experience. It won't go anywhere. So this equals 0. So I'm not asking you to prove it because we don't have enough of a framework here to prove it. But you have to acknowledge that this statement is complete as a statement in terms of the quantities that we have on the board. Because the left-hand side is well-defined and the right-hand side is well-defined. So that's a statement. The question is, How do you prove it? But that's a different question. Yeah? We can ask another question. What does this equal? Remember sigma and kappa from the last video? So I won't integrate sigma, I will integrate kappa, the thing with a sign. That's another very good question. Let me qualify it. It's not a good question, but it's a well-posed question, right? Everything here is defined. And I think the point of this segment of the lecture is to get you to sort of unlearn the preconceived notions of what an integral is and to try to think of it as something less, something more basic, something more elementary, which you understood long before you studied calculus. You understood volumes long before you studied calculus, right? On an intuitive level. What I'm trying to say is that you also understood integrals on the same intuitive level long before you studied calculus. It's a very primary, very basic concept. And so the answer here, under certain circumstances, ends up being 2 pi. Pretty, right? The question is, how do you prove it? Well, this will be on your final. How about this? We have another quantity that we know well, which is b, the curvature normal. And we can integrate that over the boundary. And the answer will once again be 0. We'll prove that as well. That's actually much simpler than proving it for the normal. This will be obvious. This will be obvious. So this one's a little bit more challenging to prove. I prove it in a paper I recently published. I'll share it with you. It's kind of fun. Very interesting question is, what do you do when the curve is not necessarily closed? How do you reduce it to the boundaries? Okay, but I think these will be able to prove. Yeah? But the takeaway here is that these statements are well defined with the intuitive concepts that we have on the board. They're at least the right questions. Okay, that completes the spiel on geometric vectors.